Okay, welcome to part 3 of these lectures on physical metallurgy of zirconium alloys. In this lecture, I'll be talking about Kearns F parameters, yield strength, radiation damage, and phase stability. We'll start with Kearns texture parameters, named after J.J. Kearns, who worked at the Bettis lab back in the 60s. Now, what we have here is basically a schematic diagram showing how a individual grain its orientation of an individual grain, the crystallographic orientation of a given grain, is related to some other direction in a material. Now, this could be a component axis. The P reference could be the longitudinal axis of a tube. Let's assume that for now. In a polycrystal, we have an arrangement of grains, and they all have different orientations. And what we want to do is we want to resolve certain properties of these grains, of the single crystal, onto the same direction of interest. So we have a whole series of different grains which all have a different value of theta, the orientation of the c-axis in this case, with respect to the reference direction. Now, Kearns chose the c-axis because the c-axis is a unique axis in the zirconium system, and for the most part, when one defines a tensor property, or when one examines a tensor property in the c-axis, it tells you a lot about the system. So what Kearns was doing was simplifying what in effect is a tensor transformation, a transformation of axes. You're going from an axis system which is a single crystal here into an axis system which defines the component. Now, he's only looking at one part of it, so he's only extracting one small part of the more complex system of equations one would need to transform all of the tensor components into a different axis system. So we're going to focus in this particular instance on the tensor property, which is parallel with the c-axis. Now, this could be a strain, or it could be a stress. And the tensor property of the single crystal in the c-axis can be transformed into a tensor property in the polycrystal by this expression here. So the tensor property which we choose from the c-axis, it could be I'd say a strain along the c-axis. When we resolve that strain onto another direction, we do so by using the direction cosines, and in this case it's a simple expression because it's cosine of theta again. It's cos squared of theta times whatever the single crystal value is. Now, it's cos squared theta. For those of you who have been familiar with vectors, when you resolve a vector into a given direction, it's only a simple single trigonometric function. It could be cos theta or sine theta or whatever it is. But when you're doing tensors, the transformation involves combinations of these vector transformations, and that's because a tensor relates two vectors. And so you have two vectors you have to deal with, and it turns out you don't have to worry about why, but if you're interested in tensors, there's lots of books on it and lots on the internet. It turns out that for a tensor property, if we're just thinking about the c-axis uniaxial tensor property, it is when it's resolved along a reference direction, which is in the component, it's simply the single crystal axis component property times cos squared theta, where theta is the angle between the c-axis and the direction of interest. Now, when you sum it for all of the grains, naturally, you get each grain has the same tensor property in the c-axis, and we simply have this expression here, which is we weight the volume fraction by the volume fraction of grains in a particular orientation. So we have a whole series of volumes of grains, or a fractional volume of grains, which have a particular angle with respect to the reference direction. So when you do that, the property here, when summed over all of the grains, which is the sum of the particular c-axis component of the tensor, when you sum that, you sum it in this way. And what Kearns did is he showed that this, or he gave this value, this sum of the volume fraction of each grain times the cos squared of the angle between the grain and the reference direction. He called this an F factor, and we know it as the Kearns F parameter. So it's probably best to illustrate what this means by giving an example. And one prime example, which is relevant to reactor operation, is irradiation growth. Now, if we carry on and expand on what we just experienced there, showed you there with the resolution of a tensor property in the c-axis, if we think about strain, and c-axis strain, we can resolve that at the reference direction with this factor. But there is also the strain coming from other directions, and in which case we have the a-axis tensor property, which is also resolved onto the reference direction. Now, what I've done here is just simply chosen the c-axis and the a-axis all to be in the same plane as the reference direction. So what this means is that this other axis doesn't figure. It's a perpendicular to the reference direction, and therefore we can just deal with these two tensor properties. So in so doing, we can relate, compute, if you like, the strain in the reference direction in terms of the cosines of the angles in this way. And what you have then is, if we put it in terms of an F parameters, the reference strain is the c-axis parameter, tensor property, c-axis strain times F, plus the a-axis strain times 1 minus F. And 1 minus F, actually F will add up to 1. So 1 minus F is simply, if F is 0.3, 1 minus F would be 0.7. Given that all of the axes, all the crystals are treated in this way. Now we can do this because, in fact, it turns out, with respect to growth, the a-axis, the strain in the basal plane is isotropic. So we can pick any strain in any direction within the basal plane, and we can rotate this, and it doesn't make any difference to the end result. So we only need one value for the a-axis tensor strain, because the strains, and in fact the strains are referred to principal axes. So how do we use this expression for the strain in terms of the F factor? Well, the single crystal strain, when you're talking about irradiation growth, is actually, we have strains 1, 1. If we consider 3 to be the axis, E3, I'll call 3 the axis, or X3 the axis parallel with the C-axis, we have, when we have irradiation growth, we have strain in the A-axis, a value of magnitude 1. In the other A-axis, and I've drawn them as orthogonal here now, as opposed to in the hexagonal symmetry, just simply, that's because that's tensors are described in terms of an orthogonal axis system. So we have 1, 1, and -2. So that what that means is that during irradiation growth, we get expansion along in the directions parallel with the basal plane, and a contraction in directions which are perpendicular to the basal plane. So if we then compute what the reference direction is, bearing in mind that we're just looking at the one component of EA, because we're basically this component of the strain is perpendicular to the plane containing this component of EA and AC. And when we do that, we end up with the reference strain is equal to -2 of EA, because the shrinkage to conserve volume, the shrinkage in the C direction is always -2 of whatever the A expansion is. And then we have the A expansion, and the A expansion is times 1 minus F, gives you the contribution into the reference direction. And when you boil it all down, the E reference, the strain in the reference direction, is equal to the A-axis strain, which would be if you have a single crystal, what you would get from irradiation growth in the A-axis, times 1 minus 3F. So by knowing F, one can then decide, or the F for a given reference direction, one can then have an idea of roughly what the growth will be. And that's it. The Kearns F parameters are used in other ways. Again, it's all about tensors, and it's all about resolving a simple resolution of one component of the tensor, and in this case it's the C-axis. And what Kearns did in his work at Bettis, he showed that if one computes the F factors for a given component, the coefficient of thermal expansion is linearly proportional to the F factor, and it changes with different temperatures, which is basically indicative of a non-linearity in the thermal expansion coefficient. As you go up in temperature, thermal expansion, the slope of the thermal expansion coefficient, or the thermal expansion coefficient itself, increases. So to move on, we're still dealing with tensors, I'm afraid to say, but tensors are great. You have to use them. They're very, very powerful tools. And again, I hope to introduce you to some aspects of tensor analysis that will make it easier for you to understand the physics of what happens during deformation. So for those of you who are mechanical engineers, you will be familiar with the von Mises yield criterion. Von Mises, for isotropic material, deduced that one could relate, for a given stress state applied to the material, one could relate the components of the stress tensor. In this case, is referred to the principal axis, which is typically when one has a single component. This is the tensile components of the stress perpendicular to a given direction. So we have 3 directions, 1, 2, 3 in an orthogonal system. And when you look at take the stress in each of the 3 orthogonal directions and compute it in this way, the product is equal to 2 times the von Mises stress, or the yield stress squared. And this is tantamount to looking at a surface in stress space, and if you have a stress locus, some value of sigma 1, sigma 2, and sigma 3 in certain axis system, wherever those 3 stresses intersect the surface, you will get yielding. In a tube, typically the stress, in a pressurized tube, the stress perpendicular to the tube surface is typically approximately 0. So in a plane stress state, we set the one stress equal to 0. So this is now a stress system defined relative to the component axes. When we deal with zirconium alloys, the material is anisotropic, so von Mises doesn't work. And for that, we then move on to what's called the Hill anisotropic condition, in which case Hill devised this other relationship, which is very similar to von Mises, but he has parameters F, G, and H, which dictate, depending on the choice of the magnitude of each one, they dictate the anisotropy that you get from yielding in the case of hexagonals. So in a nutshell, what we have are in terms of the Hill's condition, we have an equation here which tells us whenever the point at which we will get yielding for a given set of stresses, sigma 1, sigma 2, and sigma 3, it tells us that it will yield once these stresses are of such a magnitude that we exceed some condition. This condition is, in the von Mises case, would it simply be in the yield stress, the von Mises yield stress, or just simply the yield stress for an isotropic material. But in an anisotropic material, well, actually any material, one should consider this condition to be an energy condition. So at some point, when you increase the stress, you have you affect the elastic energy in the material, just basically from Hooke's law. We change the elastic energy in the system, and when the elastic energy or the work done in an elastic strain exceeds a certain value, we get yielding. Now, the easiest way to think of this yielding for the Hill's case, for the anisotropic material, is to consider the compliance tensor. So this is the Hill's compliance tensor, and if we determine what the characteristic polynomial is for this tensor, you do it in this way. You take the transpose of the stress times the tensor times the stress itself, and it gives you a value is equal to whatever the k-squared is. And when you do this transposition, you actually get this expression. So the Hill's yield criteria is actually the polynomial, the characteristic polynomial of the Hill's tensor. And from that, we can calculate what the strain rate is, because one of the characteristics of a tensor property is where, if we're in stress space, wherever the stress locus intersects the yield surface, if one takes the normal to the yield surface, that is a value for the strain rate, for the creep, in fact. So this is more involved tensor math, but it's very easy to show, but it would require a whole lecture to explain why this is so. Just take my word for it that if we're in stress space, in this case we have an actual stress and a transverse test because the radial stress is assumed to be 0. When we intersect the yield surface, at the point at which the stress locus, we increase the stress till it intersects that stress locus, and at that point we take the normal to the surface, and that normal is related to the components of the strain rate. So in order to know something about the material and how it behaves, we need to know what F, G, and H is. And in this particular case, we can determine what that is by this simply by measurement. Now, if we had a tensile data, uniaxial tensile test in each of 3 directions in the material, we can deduce F, G, and H easily. But for most reactor components, when they're made, they have a particular texture and they have a particular grain structure and microstructure. So the anisotropic response to a given stress state is often very difficult to measure. You can't simply make tensile specimens, or I guess you can make microtensile specimens out of the component, but if you have a complicated component, that's very difficult. Let's consider a tube. Although we can easily get tensile data from the transverse and the axial direction of a tube, we're missing this radial component. However, if we could measure 2 dimensions for any given applied stress in a specimen taken from the tube, in fact, we can then deduce what the F parameters are. So the best way to illustrate this is by an example, and the one I'm familiar with, and if you were present at last year's meeting, I would have showed you this, and for those, I'm sorry, I'm going to show you it again because it's such a good example. And the example of anisotropic deformation, where it's related to texture and the Kearns, Kearns texture parameters, but also the Hill's anisotropy parameters, which are kind of related. The best example I have is one dealing with a calandria tube burst strength. So what's a calandria tube? For those of you not familiar with the calandria reactor, the calandria tube, which is shown here in green, separates the hot pressure tube from the cool moderator. There are these spaces which are springs, which are coiled like garters, which are coiled around the pressure tube, and that maintains this insulating gas gap between something which is between 260 and 310 degrees centigrade, and the moderator, which is roughly at around between 60 and 80 degrees centigrade. Just for completeness, there are 380 of these fuel channels in a typical 600 megawatt reactor, calandria reactor, and 480 in a typical 900 megawatt calandria reactor. Now, pressure tube integrity is important because it's the pressure retaining component, and it sits within the core of the reactor. So for many reasons, both the irradiation properties of this pressurized component are extremely important to know, and that's why at ACL, over the lifetime of the calandria reactors, there's been a lot of effort expended on things like irradiation creep, because the component which is retaining the coolant pressure is sitting in the core. It's different from a PWR or a BWR because the pressure vessel in those reactors has a very low irradiation flux. It's basically outside of the core. Now, what happened back in the early 80s is we had these spaces. This was an early designer reactor in this Pickering A reactor. We only had 2 spaces instead of 4, like I showed earlier, and these vibrated out of place for whatever reason. They were loose, and for that reason, there was a long span which is unsupported, and the pressure tube sagged by irradiation creep. And it was in contact. Then you have this hot pressure tube which is corroding, and you have an increase in the hydrogen. This was a Zircaloy 2 pressure tube, by the way. But you have this increasing in hydrogen, and when you have a cold spot, blisters formed. And after a certain amount of time, there was the threshold for cracking was exceeded in the hydride, in the blister, and the tube failed, and there was a loca. Now, in this particular example, the calandria tube, even though it was welded, actually withstood the system pressure and maintained and held the pressure held the system pressure, basically. And that was a little bit surprising to many people, but it was a good example of how strong the calandria tube was. But the calandria tube was a different design, an earlier design, and the calandria tube withstood the system pressure because it was thick. And even though it was welded, the weld was thick. Now, at a later point in the 80s, different calandria tube design, there was another failure, and in this case, the failure was the result of a manufacturing defect. But it was also, because of the manufacturing defect, you got hydride segregation to the crack, or to the floor, and you got hydride cracking, and that tube let go as well. But in that particular case, the tube, the weld in the tube, which was thinner than we were looking at, like 1.8 compared to 1.4 millimeters thick. It was thinner, and therefore it let go under the system pressure. And so we had a catastrophic loca with a release of the coolant, primary coolant, into the calandria vessel, which contains the moderator. And the calandria tubes were thinner in this later design in order to optimize for neutron economy, and that was particularly important for Candy reactors because Candy reactors run on natural uranium. But at that time, both the utilities and the Canadian regulator were concerned about other failures happening, and about the weakness of the welded tubes. And this just shows you how the tubes are made. They're roughly 6 meters long, and they're roughly 120 millimeters in diameter, and they're seam welded. So we have this weld down the tube, and it's important to know under what conditions that weld is going to fail. So there was a concern over the burst strength in the event of pressure tube failure, and they even considered a new design option which involved seamless calandria tubes. And at the same time, considering changes in the texture to make the material stronger in the radial direction, or stronger to wall thinning. So the branch I was manager of in my latter years at Chalk River, we did the burst tests on calandria tubes, or we were certainly involved in the burst tests on calandria tubes. And this is an example of a burst test on a calandria tube, which was a fixed end burst test. And when the tube was pressurized, it let go along the weld. You can see the weld here. You can see the weld here and see where the material failed, or the tube failed, subject to an internal pressurization. However, if you take a tensile specimen and you pull the material, make the tensile specimen to include the weld, and you do a tensile test, the failure doesn't occur in the weld. The failure occurs in the main body. So the weld is actually stronger than the main body when it comes to a uniaxial tensile stress. And the best way to understand this is a great way of illustrating Hill's anisotropy. One can describe this or understand this by looking at the yield surface. So here I've plotted the yield surface in stress space, given a certain axial stress and a certain transverse stress in the tube. And I have three possible materials, components. One is the weld, and it's isotropic. So the tensile, this would be the tensile yield stress here, is the same as the axial yield stress. It's isotropic. And comparing that, we can compare that with how the main body of the tube would behave. And I've got two conditions here. One is where the radial basal texture, the Kearns texture parameter, is high in the blue line, and here in the transverse radial texture parameter is high. This is the green line. So what happens when we mechanically test these tubes with the two modes that we just discussed? So we start off, in a case of a tensile test, we have a transverse, in the transverse direction we have a tensile specimen, and we start off by increasing the stress until something fails. And the blue line represents the main body of the tube, and that's why in the main body of the tube, it's actually weaker to tensile strain than the weld, so it fails first. However, if we have a biaxial stress state, and in this case, let's consider a closed-end biaxial stress state, not necessarily a fixed end, although the fixed end is what the test was, but they're both very similar. We have a closed-end stress state, and we increase the pressure, and eventually where the stress locus, which corresponds to the stress, the internal pressurization stress, where it intersects some part of the material, you're sampling in stress space different parts of the material, it's the weld that yields first and therefore fails. So we have this nice example showing because of the anisotropy in the material, depending on the stress that you apply, the failure will either occur in one part of the tube or another part of the tube. Okay, let's move on to radiation damage. So years ago, when I first got into the business, I studying zirconium, my PhD thesis was on electron damage in zirconium at Birmingham, and I finished my PhD in 1981, and so I had a fairly acute understanding of the pitfalls of examination, TEM examination of zirconium alloys. And it was no surprise to me that actually it was a bit of a surprise, but even as late as 2014, I was at a meeting in the University of Michigan, and some guy was talking about his results with an ion irradiation, and he had examined a sample which had been ion irradiated and he examined it by electropolishing after the ion irradiation to sample the peak damage region. And he showed a figure something like this. And I immediately, for me, it's just, oh, you're looking at hydrides. Those are produced from the electropolishing. So this is the same mistake that was made way back in the 70s, where people were looking at ion irradiation. They prepared the samples, weren't prepared to consider, didn't have any experience in that time, and didn't understand about what happens if you're not careful about how you prepare a sample, and you get a lot of stuff which looks like dislocation loops, but it's not. And in this particular case, they thought that there was C-component loops, which it wasn't. It was, you could basically have nothing there at all, and you're just looking at hydrides formed during preparation. So here's an example where I prepared a sample of zircaloy 2, where I simply oh, actually, this is a, I think, yeah, I must have, when I prepared this slide, I must have made it with this, I must have picked up a sample or an example from pure zirconium. Anyway, one can get this very similar hydride thing without even trying. So in fact, if you don't try, you will get hydrides formed. So here's another example. This is something I made up specifically just to answer people's questions about artifacts that are produced. And this is what typically what you get in zircaloy 2 at a particular orientation. You get these splatters of what looks like damage, but it's actually little precipitates, hydride precipitates on the surface. And if you have single crystal, you get much bigger hydrides. So I've seen so many examples over the years where people are studying hydrides and talking about bulk hydrides, and then they prepare a sample and they'll show something like this and say, aha, look at this, we have this hydride forming and it punches out dislocations, shear dislocations, and this is, and then they come up with all kinds of models and theories about what happens. And missing, for the most part, the fact that this is probably a hydride created by electropolishing. And the stresses arise because you have a site on the surface for whatever reason which is highly reactive, and that's why you get the hydride formed there, because you're creating a lot of hydrogen and you're pushing a lot of this hydrogen into the material. So it's a source. You actually have a source of hydride at this point, and no wonder you get a high stress induced. But that has nothing to do with the bulk behavior of the hydrides. So what I've found over the years is if I don't see somebody who says, and we know that this is not a surface hydride because we did the appropriate stereomicroscopy, I don't believe anything of what they say. I'm getting off target a little bit because I really want to talk about radiation damage. And here's an example just to illustrate what radiation damage looks like when atoms are displaced. In lecture 1, I talked about displaced atoms, but I didn't talk about how they cluster together, and they form platelets when they do cluster together, which are called dislocation loops. So in an unirradiated material, you might have a nice annealed sample with very little, few defects in there, and then after, maybe a few hydrides, but after irradiation, surface hydrides in this case, but after irradiation, you get these clusters of displaced atoms, which are dislocation loops. So to illustrate that, I've shown it here in the case of zirconium. I've shown an example of a typical prism dislocation loop, so typically prisms like this. In this case, I'm illustrating an interstitial loop. So if we accumulate atoms on a given plane, we end up with a platelet which stretches out the lattice. But that doesn't mean to say that all prism plane loops are interstitial. In fact, they're not. Very often they're vacancy. Probably there's always a mix of interstitial and vacancy. And here's a vacancy defect. And for this case, on the basal plane, the vacancies accumulate, and they give rise to a contraction of the lattice perpendicular to the c-axis. And if you remember my example with the Kearns texture parameter, this is the kind of behavior which is more or less similar for all single crystal materials irradiated. You get a contraction in the c-axis and expansion in the a-axis. And to conserve volume, the contraction in the c-axis has to be double whatever the expansion is on any one a-axis. Now, that was kind of considering a pure single crystal with no defects in it. But what actually happens in practice is that if you have a core work material, this core work material has dislocations in it, and if you have screw dislocations in there, you'll get these point defects which may nucleate at a certain point on the screw dislocation, rather than creating a separate loop in the middle of nowhere, which is a little bit more difficult, but having a dislocation cuts out the nucleation step, so that when you irradiate a sample with screw dislocations, in this case a C component or C plus A screw dislocation, you get this nucleation or accumulation of point defects, which gives rise to what's called helical climb. And this is just the same as the loop formation, except the nucleation stage is made easier by having the dislocation. So in irradiation, this is electron irradiation example, something I did in the Max Planck Institute way back in the 90s. I took a C plus A dislocation. This is in the high voltage microscope. And then after irradiation, in this particular case, I can't remember how much I irradiated it to. 10 to minus 3 dPa per second. We're probably looking at 20 dPa here, 10 to 20 dPa. What we end up with is this helical climb, which is viewed here edge on. Now, it's often difficult because there's a whole bunch of other damage going on, obscuring the contrast. But if we go to a high temperature irradiation, and where I already have a C component loop, so imagine this is a loop which is viewed edge on, and now we look at the loop, but looking at it from top down. This is a loop that our sample I specially prepared, which had been irradiated with neutrons. It's a vacancy loop, and I'd done the analysis, so I knew it was a vacancy loop. And then I put it in the electron microscope and re-irradiated it. And this is what you get. Shit. Okay, that's what you would have got. But I'm doing a recording here. I'm sorry. I guess the media doesn't work when I'm in record mode. Anyway, so what you would have seen there is the loop grow. So in the live presentation, I would demonstrate a video showing that loop expanding and growing as you irradiate it with electrons. I mentioned about core work structures. I mean, often if we have a core work structure, whether it's a zircaloy or a zinc niobium, it's typically, because it's heavily deformed, typically the grains are flattened into platelets, pancakes like that, and they contain a very high density of dislocations. So if we want to use TEM to look at the evolution of real components, real engineering alloys, and in this case a core work stress relief annealed material, very difficult to make any quantitative assessments. So here we have a complicated mess, and then we irradiate it, and it looks like an even more complicated mess with even the dislocations being obscured. The C component structure is a little bit easier because we don't have the contrast from the A-type structure. The A-type loops, those are the ones on the prism planes, they're much more higher density, there's many more of them, and they form very rapidly during irradiation and quickly saturate at a high density. But the C component structure we can study with some clarity, and this is an example of what the C component structure looks like. This is in I think again in zinc niobium. So we have these C component dislocations, and this is the C axis. So these segments here have a strong screw component, and when you irradiate them, you get a lot of these helical climb on these dislocations, and we end up with a structure like this. It's still very difficult to make anything quantitative out of this, because it's just again, it's a cleaner mess, but it's still difficult to quantify what is happening. And that's why many years ago, when I first joined AECL at Chalk River, I decided that the only way to do anything reasonable with these materials was to use X-ray diffraction. So if we use X-ray diffraction, one can monitor the evolution of the structure, naturally using TEM in order to interpret the X-ray diffraction results. But this is an example on the left-hand side here. This shows some X-ray diffraction data measurements as a function of fluence for a recrystallized annealed guide tube. And what you see here, if we look at this top line here, which is the prism 3O bar 3O reflection, at the early onset of irradiation, we get a very rapid increase in the line broadening, which is really the same as the dislocation density increase, and it very quickly reaches a kind of a more or less saturated condition. The C component structure, though, there's some change in line broadening, which could be just simply residual stresses or whatever, but it takes a while before the C component structure evolves, and this point here is known as breakaway growth. So at some point, at some fluence, you get enough the conditions are right where basal loops will form, and we get this breakaway condition. On the right-hand side here, I'm comparing this breakaway condition again as a function of fluence, and comparing about with what you would see for an equivalent material, in this case stress relief annealed. That's not a zirconium pressure tube. In fact, this is for a zircaloy 2 pressure tube. So that's an error. I'll have to change that. Apologies. But a zircaloy 2 pressure tube taken from the SGHWR in the UK, after it broke down, I was able to get some samples and examine them. And what we have for the zircaloy 2 pressure tube, we have a very rapid increase in the C component density, which occurs right from the get-go. So there's no incubation, and that's because we have these C component dislocations already present from deformation, and they the loops evolve, nucleate on these dislocations and evolve very rapidly. So we, in terms of radiation growth, we end up with a very much faster radiation growth in the case of the cold work material. Now this is the zirconium pressure tube. Similar effects. If you look at zirconium pressure tubing, we get this rapid increase in the A-type damage, and it saturates at a very low fluence, roughly 2 times 10 to the 24 neutrons per meter squared, which should be 2 or 3 times 10 to the 20 neutrons per centimeter squared. And the C component structure evolves over a much longer period, like this. And the green line here is what the original structure would have been, so the unirradiated material. Okay, move on. Again, this is all about zirconium and different things that occur during, in this particular case, during radiation. The next thing I want to talk about is phase stability. So when I first joined AECL, we had calandria tubes in the reactor, and they were typically operating at about 60 degrees centigrade, roughly between 60 and 70 degrees centigrade. And what was observed is for zircaloy 2 calandria tubes, both the Lavis phase ZRCR Fe2 precipitates and the ZR2 NiFe precipitates, which I incorrectly labeled Zintel phase. It's roughly reasonable, but not exactly, strictly speaking, correct to call them a zintal phase. But there were these other precipitates, and they both became amorphous at low temperatures. So something more relevant to the U.S. industry is at higher temperatures, around about 300 degrees C, not the zinc-nickel precipitates, but the zirconium ion precipitates, they became amorphous. And it was something unusual in that there was the amorphous layer started from the external part of the precipitate and advanced inwards with increasing fluence. And what you ended up with is the amorphous region was depleted in Fe, in ion, so you have this ion diffusing out. So ion dispersal from any component, whether it's as a phase, a compound, or whether it's as an impurity, typically the rule of thumb, when you irradiate any material with ion in it, the ion just gets spread everywhere. So this ion was diffusing out, and the way I interpreted this was the decrease in the stoichiometry, because ZrCr2 is essentially a highly stoichiometric material. The decrease in the stoichiometry by the ion departing meant that these material then became amorphous. This is kind of schematically shown here of what happens. You start out with the precipitate. During irradiation, you get this layer at the surface which is depleted in ion, but also becomes amorphous. Eventually, the whole thing becomes amorphous, but it's still dissolving, and eventually it's mostly gone because the ion is getting dispersed everywhere, but also the chromium is getting dispersed. So one of the observations I had way back in the early 90s was that if we looked at one of these zirconium ion precipitates and did a scan outside of the precipitate, one could see variations in the impurities, and showing that the material coming from the precipitate was being preferentially eroded in certain layers, and these were parallel with the basal plane. And this erosion, or this structure parallel with the basal plane, corresponded with where you see C-component loops. So there was an indication here that the loops were stabilized by the increasing in the impurities in the matrix. A couple of asides I should mention is when I first arrived at Chalk River, which is in 1984, I should mention that the technician who worked for me when I first arrived was a guy called Ross Gilbert. But prior to my arrival, Ross was the first person to notice that there was an amorphous transformation of the zirconium ion particles, and that this transformation also had corresponded with a depletion of ion. Kind of irritatingly, Ross was concerned because in late '83, somebody from GE had come and visited the lab. Ross had shown him his results, and they got very excited, and then asked for Ross to send them examples of what he found, and he did. And I guess Ross was concerned that these guys were going to go and take credit for it, and they did. They went off and they took credit for it. Little did they know that we'd already published. When I arrived, very quickly we had a letter to the editors to describe the structure. But what was interesting is that they didn't acknowledge, and it was Ross, not me. It was Ross that needed the acknowledgement, because he was the first one. As a technician, he prepared the samples and he observed. He said, "Hey, look at this. We have this amorphous transformation." Another factor, another interesting story is in CEA, the French tried to reproduce some of these effects, these amorphous effects, with ion irradiation. So there's some ion irradiation, and lo and behold, in one of the examples they saw some amorphous transformation at one side of the precipitate, and they said, oh, okay, this must be an example of ballistic mixing. But what they failed at the time to understand was that, no, they were looking at the ion damage from the ion milling that they used to create the samples. So the ion milling was performed at room temperature, and the precipitates which were sticking out of the surface became amorphous, where the ion beam, which was a slanted, like glancing angle ion beam, where it intersected the precipitate, and that formed the basis of a lot of theory going on about ballistic mixing and stuff like that, which I never believed. But you know, anything can happen. But it turned out, to their credit, they reported years later that they found that ion milling created amorphous transformations. Basically, it was an artifact. So just like the hydrides, this, you have to be very careful about amorphous structures, that you have to be careful that you understand how they were prepared. And if you're preparing them in a fib, for instance, or with an ion mill, any type of ion mill, it's possible that you could be creating the amorphous phase, and it's not really that from irradiation. So having a control experiment is always important. So if you're doing an irradiation experiment, have that control, prepare everything the same, and compare the control with the irradiated sample. So finally, I'm not sure I'm finally, yeah, I guess I am finally. For completeness, one of the things that's peculiar about zirconium is the formation of precipitates, these little black dot contrast, arrow contrast here. When you radiate zirconium, you create these little niobium precipitates in the alpha phase, because the alpha phase is slightly saturated, oversaturated in niobium. Even though it's only about 1%, the equilibrium state concentration of niobium in the alpha phase is about 0.3 weight or atomic percent either way. But after fabrication, because it's a very sluggish transformation, you end up with a supersaturation or oversaturation of niobium, and when you irradiate, it precipitates.